Alright, what's going on, everybody? This video we're gonna do problems dealing with work. So let's go ahead and get started. So we have here in the SI metric system, and then we have the US customary system. So mass in the metric system, mass is measured in kilograms, US pounds. Displacement is in meters, US feet. Time is measured in seconds in both. And then in the metric, force is measured in newtons, US, and pounds. And so if the force is measured in newtons and the D, which is distance, in meters, then the unit for work is a Newton meter, which is called a joule, and that's written as a capital J. And then we have, if F is measured in pounds and D in feet, then the unit for work is a foot-pound. And work is equal to force times distance, which you can see right here is force times distance. So let's go ahead and take a look at our first example. So now the first two examples, they're similar to each other. How much work is done in lifting an object, and the first, they're both work the same. It's just that the first one is in the metric system and the other one is in the US customary system. So let's look at this first example. How much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? All right, so remember, work is equal to force times distance. So we're in the metric system, so force is equal to mass times the acceleration due to gravity, G. All right, and that is equal to 1.2, which that's the mass, 1.2, times, and then what's the acceleration due to gravity? That is 9.8. All right, that's something that you're supposed to know. And so when we multiply that, that gives us 11.76 newtons. All right, so this is our force, the 11.76. So now we can calculate the work, which is force times distance, the distance we have to lift the object. So work is equal to 11.76 times the distance. Well, how far did we have to lift it? 0.7 meters. So that's times 0.7, and that gives us 8.2 joules. And so there's your answer for that one. All right, so for the next problem, how much work is done in lifting a 20-pound weight 6 feet off the ground? Well, this is going to be same thing, work equals force times distance. Now, keep in mind, if you look up here, remember, if F, or if the force is measured in newtons, so the force excuse me. So if the force is measured in newtons, okay, so keep that in mind. The force is measured in newtons. That's the metric system. Well, look what they gave us in the problem. They gave us 1.2 kilograms. They didn't give us the force. We had to calculate it. Okay, the force is measured in newtons. So to get the force, we had to multiply the mass in kilograms times the acceleration due to gravity to get our newtons. All right, but notice what it says here. It says if F is measured in pounds, all right, we're in the US customary system, so you can see force is measured in pounds, and you can see here this is a 20-pound weight, so this is the force. And then the 6 here, that's our distance D. So we just plug it straight into the formula. So that's going to be 20 times 6, which is 120 foot-pounds. And there's your answer. So you have to do a little more to the problem when you're in the metrics, okay? All right, so let's look at this next problem, or let's look at this. So for a variable force, what if we have a variable force? Then the work is equal to the integral of f of x dx evaluated from A to B. All right, that's for a variable force. So let's look at this. So the variable force, that's going to, our force, notice it's a function here. So it says when a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equal 1 to x equal 3? All right, so what does it say to do? Well, it says to integrate the function. So we're going to integrate this right here. And we're going to integrate it from 1 to 3. That's our limits, A and B here. And so the work is the integral 1 to 3 of x squared plus 2x dx. So that's going to be 1/3 x cubed plus x squared from 1 to 3. All right, so what do we get when we evaluate this? That's going to be 1/3 times 3 cubed plus 3 squared minus, and then 1/3 times 1 cubed plus 1 squared. And when you punch all that into your calculator or do the arithmetic, you get 50 over 3 foot-pounds. Because notice we're in pounds and feet. All right. So that's a variable force. That's not difficult at all. You just got to integrate. I mean, I guess sometimes, the function you have to integrate, it could be a difficult function to integrate, but in this case, it wasn't. All right, let's look at the next one. All right, so here we have Hooke's law. So it says the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So we have f of x is equal to k times x, where k is a positive constant. It's called the spring constant. All right, so let's use Hooke's law to solve this next problem. All right, so it says a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? All right, so the thing you have to do here is remember you have f of x is equal to k times x. So what we have to do is we have to figure out what k is. That's what we have to calculate. So we know that if we plug in you've got your spring here. Let me see if I can draw that a little better. All right, so you got a spring here, and its natural, let's say its natural length is this. This is 10 centimeters, and we want to stretch it to 15 centimeters, okay? So that means that we're stretching it an extra 5 centimeters, okay? And to hold that spring to this distance here requires 40 newtons of force, all right? So that 40 newtons of force, that's stretching it an additional 5 centimeters. and we know that 5 centimeters is equal to 0.05 meters. Because if you remember at the first, when we're in the metric system, our force is in newtons and our distance is in meters. So we have to convert the 5 centimeters to meters. All right. So what it's saying is if we take this function and we evaluate it at 0.05, that should equal 40 newtons, which this tells us that 0.05 times K is equal to 40, which means K is equal to 40 over 0.05, which is equal to 800. So that's K. So that means we have f of x is equal to 800x. All right. Now we just integrate. All right. So we're going to integrate this function 800x dx. Now, what's going to be the limits on our integral? Well, what does it say here? It says how much work is done in stretching the spring from 15 centimeters to 18 centimeters. So you can see here we want to stretch this all the way out to 18 centimeters. So what are we doing? Well, if you look at this, we're measuring from the natural length out to 18 centimeters. So that's going to be 8 centimeters. So remember, its natural length is 0. And so if we're going to go stretch it from 15 to 18, you see that? From 15 centimeters to 18 centimeters. Well, where are we starting? We're starting at 5 centimeters, which we know that is 0.05, and we're going out to 8. We're going what? We're going out to 18 centimeters, which is an additional 8 centimeters. You see that? We stretched it an additional 5 centimeters. So there's your 0.05. And then out to an additional 8 centimeters past its natural length. And so 8 centimeters is equal to 0.08. meters. And so that would be 0.08. And so here we get 400x squared from 0.05 to 0.08. And so this is going to give us 400 times 0.08 squared minus 400 times 0.05 squared. And that ends up being 1.56 joules. All right. So I hope that makes sense. Just remember, you have to, when you're calculating your limits, you've got to do it the distance from its natural length to get your limits. All right. So how about this one? We have a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? Well, let's draw a picture first. All right. So here's the building, and here's the cable hanging off. Now, when you're working these problems, and this is going to go for the rest of the problems that we're working, don't consider the entire rope when you're setting up your function. What we want to do is we want to take just a little piece of the rope. Okay? Take a little piece. And the width of that piece there is delta x. And that piece is x feet from the top. And keep in mind, the entire rope is 100 feet long. All right, so remember, we want to find the work. So let's calculate the work done to just pull up this little piece right here that has a width of delta x. Okay, calculate the work done for that. So remember, work is force times distance, and we're in pounds. So we need to get the weight of this little piece here. All right. So it tells us a 200-pound cable is 100 feet long. So 100 foot of cable, that entire 100-foot cable weighs 200 pounds. So this tells us that the cable weighs 2 pounds per foot. All right. So if we have a piece of rope that's 1 foot long, that weighs 2 pounds. If we have a piece of rope that is 2 feet long, that weighs what? 4 pounds. If we have a piece of rope that's 3 foot long, then that rope weighs what? 2 times the 3 feet, which is 6 pounds. So the weight of a piece of cable, I might have said rope. If I did, I meant cable. But the weight of the cable is 2 times whatever the length of that piece of cable is. Okay? So that tells us that the force of this little piece is the 2 pounds times the length of that cable. And what's the length of that cable? Delta x. That's the force. That's how many pounds it is. That's the force. And then the distance we want to pull this little piece up. We're not looking at the whole rope, just this little piece. The distance we want to pull it up, the distance is equal to what? X. All right, so remember, work is equal to force times distance, and we're going to integrate it. So the force times distance, so that's going to be 2 delta x times x. So that's going to be 2x, and remember, delta x is equal to dx. All right. Now we need to figure out what our limits are. All right. So remember, this little piece of rope here, I keep saying rope, I mean cable. Okay. If I say rope again, just know it's cable. All right. This little piece of cable here, I've got an infinite number of those pieces. Okay. So what I'm going to do is I'm going to sum up the force of each of those pieces. So I need to go from the piece that's right here at the top. So if I have a piece right at the top, piece of cable there, how far do I have to pull that up? Well, that's 0 feet. Okay. And then the piece down here at the very bottom, how far does that one have to be pulled up? Well, it has to be pulled up 100 feet. And so there's my limits. And so now all we have to do is integrate this thing. So that's going to be x squared from 0 to 100 which is 100 squared minus 0 squared, which that is going to be 10,000 foot-pounds to pull the entire rope up. All right, so I hope that problem made sense. Just remember when you're setting up your function here, you know, to get this and this, just consider one little piece of the cable. Just consider one piece and get what that one little piece, the work for that one piece. And then when you go from 0 to 100, from the one that's at the very top to the one that's on the very bottom, you're summing up all the work done for all those pieces on that cable. All right, so keeping that in mind, let's look at this next example. All right, so we're going to be pumping water out. And for this problem, this is in metric, and then the next problem is going to be in the U.S. customary system. So you can see the difference in finding the work done to pump water out of a tank. All right, so it says a tank has the shape of an inverted cone with a height of 10 meters and base radius 4 meters. If it is filled with water to a height of 8 meters, find the work required to empty the tank by pumping all of the water to the top of the tank, and the density of water is 1,000 kilograms per cubic meter. All right, so let's draw a picture. So I've got an inverted cone. And we know the height of the entire thing is 10 meters. And I've got the water right here. There's the water. And we know that's filled up to 8 meters. That's what it tells us here, the 8 meters here. And what I want to do is I want to take just a little slice of this. Okay. We're not gonna consider all the water. We're just gonna consider a slice of it. And we're gonna get our function based on that little slice. And the width of that slice is delta x. All right, so let's finish drawing this out. The distance from the top down to that little slice, we'll call that x. And then we know the distance from the top to the water is 2 meters, because we know the height of the water is 8 meters, and if the whole tank is 10 meters, we know that's 2 meters there. And then we know the distance from here to here is 10 minus x, because if the whole thing's 10, if this is x, this is 10 minus x. All right, and then this is the radius of that little circular slice that we're taking out. All right, so remember, work is force times distance. Force times distance. So work is force times distance. And remember, to get the force, that's mass times the acceleration due to gravity. That's what we've got to find. Okay, so how do we get that? All right, how do we go about getting that? Well, to figure out the mass, well, it says the density of water is 1,000 kilograms per cubic meter. All right, so I need to figure out the volume of this little slice and multiply it times 1,000 to get what? To get the mass. okay? The mass, keep in mind, the mass is the density times the volume of the piece. That's going to give us the mass of it. So I know the density, that's 1,000 kilograms per cubic meter. I need to figure out what the volume is. Well, the volume is, well, what's the volume of that thing? Remember, it's like a little cylinder, okay? It's like a little cylinder. So it's going to be the area of the base times the height, right? The area, because it's a circular base, okay? Think of a Coke can. No, that's not drawn very good, but think of that. What's the volume? It's the area of the base times the height. That's the volume, and that's what we have here. It's just that it's not as tall, okay? All right. So I need to figure it out. So what's the area of the base? Well, it's pi r squared, right? Pi r squared, and then times the height. Well, to figure that out, I need to get everything in terms of x. See, this radius right now is r, but I don't want r. I want this radius in terms of x. So we can do that by saying r over 10 minus x is equal to what? 4 over 10. All right, so how did I get that? Well, I just used similar triangles. See, the radius of the smaller one over the height, you see that, is equal to the radius of the larger one, which this radius here, remember that's 4. They gave us that in the problem. And base radius 4. So that 4 over the entire height, which is 10. And so I get r is equal to 2/5 times 10 times 10 minus x. So that's the radius. And so the volume is pi r squared. So that's 2/5 times 10 minus x squared. This is your radius. Remember this right here, that's r. So that's the area of the base of that little slice right here. So that's the area of the base times the height. What's the height? It's delta x times delta x. And so that's going to give me volume is 4 over 25 pi times 10 minus x squared delta x. So that's our volume. Okay. So now to get the mass, remember, that's the density times the volume. So that's going to be 1,000 times 4 over 25 pi times 10 minus x squared delta x. And so the mass is equal to, and that's going to end up being 160 pi times 10 minus x squared delta x. Okay, I just multiplied the 4 over 25 times 1,000 gives me 160. So now we can get the force, which is m times g, mass, which is 160 pi times 10 minus x squared delta x times the acceleration due to gravity, which is 9.8. And this is multiplied. And so that's going to be force is equal to 1568 pi times 10 minus x squared delta x. Okay, so I just multiplied the 9.8 times 160. And so now I'm ready to calculate the work. And it's going to be the integral. And remember, work is what? Force times distance. So that's going to be force, which is 1568 pi times 10 minus x squared delta x. Well, I'm sorry. We'll do dx, all right, times what? The distance. So remember, this is the force, and then times the distance. Well, what's the distance that little slice has to come up? It has to come up x, right, to get over the top. You see that? So that's going to be times x. Now we need to get our limits. So just like with the rope, think of an infinite number of little slices in here. So the slice here at the very top, how far does it have to come up? 2 meters. And then the slice at the very bottom, how far does it have to come up? It has to come up 10 meters. All right. And so that's going to give us 1568 pi from 2 to 10. So I'm pulling out the constant terms. And then that's going to be 100 minus 20x plus x squared times x dx. All right, so where did that come from? Well, that 10 minus x squared, remember that's just 10 minus x times 10 minus x. I just fold it out. And now I'm going to distribute the x. And so that's going to be 1568 pi from 2 to 10 of 100x minus 20x squared plus x cubed dx. And now we're ready to integrate this thing. So that's going to be 1568 pi times, and that's going to be 50x squared minus 20 over 3x cubed plus 1/4 x to the 4th. And that's going to go from 2 to 10. And so whenever you do that out, I'm not going to plug all that in. You plug the 10 in, plug the 2 in, subtract them, and then multiply times this 1568 pi, and that's going to give you 3.4 times 10 to the 6th joules. That's written in scientific notation. All right. So just remember, the whole key to this is getting this right here, force times distance. What do you need to get the force? And to get the force, we had to do all of that to get the force. We had to calculate that. Now, it would have been nice if they would have just came out and said, here's the force, but they didn't. Okay? All right, so that's working a problem where you're pumping water out, and that's using the metric system. Now, let's work this last problem here of pumping water out of a swimming pool, and everything's in pounds and feet. All right, so we have a circular swimming pool, has a diameter of 24 feet. The sides are 5 feet high and the depth of the water is 4 feet. How much work is required to pump all of the water out over the side? Use the fact that water weighs 62.5 pounds per cubic foot. All right. So they don't come out and tell us how much that slice of water weighs. They just tell us how much it weighs per cubic foot. So we're going to have to actually figure out the force on this. So let's draw a picture. Not a very good circle there, is it? Or ellipse. All right, so we know this thing is 5 feet tall. The water is right here. We know that's 1 foot to the top, from the top of the water to the top of the tank. And we need to get a slice of this. All right, and the distance from that slice to the top is x, and we know this is 5 minus x. And what's nice here is we know that is 12, right? This is 12. We know the radius because they tell us the diameter is 24 feet. All right, so remember, work is force times distance. So we need to come up with force. Now remember, in U.S. customary system, the force is in pounds. All right. So how much does this little slice weigh? Well, what's the height of that slice? It's delta x, right? That's what the height of it is. So how do we get the weight of that little slice there? Well, it's going to be the 62.5 times the volume of that thing, right? Because it's 62.5 pounds per cubic foot. So we need to know how many cubic feet this slice is and multiply it by 62.5. So the volume of that little slice, well, it's what? Pi r squared times the height, right? And so pi times the radius squared times the height. And so the volume times the height. So that's 144 pi times delta x. And so the force is 62.5 times the volume. And that is going to be 9,000 pi delta x. So now we got the force. And so now work is going to be the integral, and it's going to be the force, which is 9,000 pi dx times the distance we have to lift this little slice to the top, which is x. All right. And now we need to get our limits. So remember, just like before, we got to take the very top slice. How far does that have to go up to get over the top? 1 foot. And then the one on the very bottom, that slice on the very bottom, how far do we have to lift that up to go over the top? 5 feet. And so this is going to be 9,000 pi 1 to 5 x dx. And so if we integrate that, that's going to be 4,500. Let me write that 5 a little better. 4,500 pi x squared from 1 to 5. Okay? Remember, you add 1 to the exponent, that's 2, divide by the new exponent, 9,000 divided by 2 is 4,500. So that's going to be 4,500 pi times 5 squared minus 1 squared. And that is going to give us 108,000 pi foot-pounds. And that's your answer. So remember, when you're talking about pulling up ropes or cables or whatever, or you're talking about pumping water out of a tank, don't think about the entire rope or don't think about all of the water. Set up your function, your F times D, based on a little slice of it. And then that's what you're doing with your integral, is you're summing up all those little slices from, whatever to whatever. In this case, 1 to 5. All right. That's all it is. And that's usually the hardest part for students is coming up with this part right here. It's coming up with that. But just think, you need force times distance. What do you need to do to find the force? What do you need to do to find the distance? And that's all you're doing, and you're doing it based on just that one little slice there. All right, so I hope this video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see y'all in the next one. Later.